Hey there, I'm Ben. Have you ever wondered what happens to something when you're not looking at it? For example, if I were to close my eyes right now, could something like this happen? Well, probably not, but it's possible. This question has been around for a really long time. Philosophers since the 1700s have asked, if a tree falls in a forest and no one's around to hear it, does it still make a noise? And with an actual object, it's the same idea. Is it still there when you're not looking at it? In order to answer this question, we need to understand Heisenberg's uncertainty principle, an integral part of quantum mechanics, the physics of subatomic particles. Heisenberg said that we can know an object's velocity or its position, but not both at the same time. In other words, the more accurately we know how fast this cat is moving, the less we know about where it is. But that's only true if the cat is a subatomic particle, and that's one of the things that's so strange about quantum physics. It doesn't work in the way we expect it to. Let's take a look at an atom, for instance. Here you can see the classical model of an atom. You can see the electron orbiting the nucleus like a planet orbiting a star. But hold on, we know that electrons move at the speed of light. And quantum mechanics tells us that if we know how fast an object moves, we can't know where it is. That's where the Schrödinger model comes in, a more updated and recent model of the atom that looks like this. Here we can see what scientists like to call an electron cloud. It's called that because we don't know where the electron actually is. It could be anywhere within the shaded area of the cloud at any given time. The cloud is an area of probability. That is, statistics tells us that the electron is likely within that area and not anywhere else. And here's where things get really weird, because it turns out that not only is the electron somewhere within that area of probability, it's simultaneously everywhere within that area. What the? Sorry about that. This stuff is really weird. It's called quantum superposition. And the idea is that an unobserved particle is in every possible state at the same time, whether it's position, velocity, or any other state allowed by the uncertainty principle. But when we do look at the particle, it chooses a certain state to be in. To better explain this, let me introduce my sister, Jenny. Jenny's in 5th grade, meaning she's got big girl responsibilities like school and homework and ballet practice. Every weekday, she goes to school from 8. What's going on? Oh, not every weekday, I guess. I mean, what if she's sick? Or what if there's a snow day? Over the course of a school year, we can record where Jenny will be at a certain time, say noon. Now that we have our data, let's graph it based on how far away Jenny is from home. This graph is called a wave function. On one end, you can see all the times Jenny stayed home from school. Here's the time Jenny missed school for a ballet performance, and here are all the times she was at school. As you can see, it's much more likely that she'll be at school at any particular time. So, we've been able to predict where Jenny will be in real life, just like we were able to predict where an electron will be in an atom. An electron would be in all of these places at once. But clearly Jenny can't be at home sick, at school, and at ballet all at the same time. So how did physicists prove superposition? Well, they came up with a famous experiment called the double slit experiment. It uses, you guessed it, 2 slits in an opaque material. A light source is used to send photons, particles of light, through the slits. Now, obviously, if photons are particles, they'll just go through the slits and end up on the other side. We would expect to get an image like this, but instead, scientists got this. How is that possible? Unlike electrons, photons exhibit superposition in wave-particle duality. That is, they can act like both a wave and a particle when we're not looking. When waves propagate through a small opening, they spread out and interfere with each other, causing the weird pattern we saw. But hold on, what happened to the photons? It turns out that if we actually measure the photons and see which slit they go through, we get this. We did nothing different except look at the particles. And that's one of the incredible things about nature and quantum mechanics. Nature does things behind our backs, and just by looking at them, we force it to take a single shape. Superposition is perhaps the most important concept in quantum mechanics. It underlies the very basis of how subatomic particles interact. It's the reason we have both classical and quantum physics. Scientists just can't grapple with the idea that this cat can be both dead and alive. Huh. Wonder what would happen if I stopped looking at it, like put it in a box or something.